Batch normalization. Batch normalization in deep learning. AI intermediate level. Introduction. Training deep neural networks can be challenging. As data flows through many layers in a neural network, the distribution of inputs to each layer can change during training. This phenomenon is known as internal covariate shift. When this happens, training becomes slower, unstable, harder to optimize. To solve this problem, researchers introduced batch normalization. Batch normalization is a technique used to stabilize and accelerate neural network training. It is widely used in deep neural networks, convolutional neural networks, CNN, recurrent neural networks, RNN, computer vision models, natural language processing models. Understanding batch normalization is important for building efficient and stable deep learning systems. What is batch normalization? Batch normalization is a technique used to normalize the inputs of a neural network layer during training. In simple terms, batch normalization equals adjusting layer inputs so they have stable mean and variance during training. Example concept. Layer input means normalize values means stable training. This helps neural networks learn faster and more reliably. Why batch normalization is important? During training, the distribution of activations in neural networks can change. Example concept. Layer 1 output means distribution changes. Layer 2 input means unstable training. This causes problems such as slow training, gradient instability, sensitivity to initialization. Batch normalization stabilizes the data flowing through the network. Example concept. Normalize inputs means stable distribution means faster training. Core idea of batch normalization. Batch normalization standardizes the inputs of each layer. This means adjusting values so that they have mean close to 0, variance close to 1. Example concept. Raw activations means normalization means standardized values. This normalization is performed for each mini batch during training. Mathematical representation. Batch normalization standardizes each batch using the following equation. Hat x equals frac x mu underscore b sqrt sigma underscore b squared plus epsilon, where x equals input value, mu b equals mean of the batch, sigma b 2 sigma b 2 equals variance of the batch, epsilon equals small constant for numerical stability, x equals normalized value. After normalization, the model applies scaling and shifting. Y equals gamma hat x plus beta, where gamma equals learnable scaling parameter, beta equals learnable shifting parameter. These parameters allow the model to learn the best distribution. Where batch normalization is applied. Batch normalization is usually applied after a linear transformation and before the activation function. Typical layer order. Linear transformation. Down pointing arrow. Batch normalization. Down pointing arrow. Activation function. Example concept. Dense conva layer means batch norm means ReLU. This improves training stability. Batch normalization workflow. The batch normalization process works like this. Input batch. Down pointing arrow. Calculate batch mean. Down pointing arrow. Calculate batch variance. Down pointing arrow. Normalize inputs. Down pointing arrow. Scale and shift values. Down pointing arrow. Pass to activation function. This process repeats during each training iteration. Batch normalization during training versus testing. Batch normalization behaves differently during training and testing. Training phase. During training, batch statistics, mean and variance, are calculated. Normalization uses the current mini-batch. Example concept. Training batch means calculate mean and variance. Inference phase. During testing, stored running averages are used. Batch statistics are not recomputed. Example concept. Use learned statistics means stable predictions. This ensures consistent model behavior. Benefits of batch normalization. Batch normalization provides several important benefits. Advantages include faster training, improved gradient flow, reduced sensitivity to weight initialization, improved model stability, slight regularization effect. Example concept. Batch normalization means faster convergence. It also allows using higher learning rates during training. Example Python code. Keras. Batch normalization can easily be implemented using Keras. Example code. From TensorFlow. Keras. Models import sequential. From TensorFlow. Keras. Layers import dense. Batch normalization. Model equals sequential. Dense. 128. Batch normalization. Dense. 64. Batch normalization. Dense. 10. Activation equals softmax. This adds normalization layers between neural network layers. Real-world applications. Batch normalization is widely used in modern deep learning models. Computer vision. Improving CNN training for image recognition. Natural language processing. Stabilizing deep transformer models. Speech recognition. Improving training of deep audio models. Autonomous vehicles. Training deep perception systems. Healthcare AI. Stabilizing training for medical diagnosis models. Limitations of batch normalization. Despite its advantages, batch normalization has some limitations. Challenges include performance may decrease with very small batch sizes. Extra computation required. Not always ideal for sequential models like RNNs. Example concept. Small batch size means unstable statistics. Alternative normalization methods such as layer normalization, group normalization, are sometimes used. Concepts learned from batch normalization. Understanding batch normalization helps learners understand. Checkmark how neural network training becomes more stable. Checkmark how internal covariate shift affects deep learning. Checkmark how normalization improves gradient flow. Checkmark how deep models train faster. Checkmark how modern AI architectures are optimized. Batch normalization is one of the most important techniques used in modern deep learning systems. Simple definition. Batch normalization. A technique that normalizes the inputs of each neural network layer to stabilize and accelerate training. Final summary. Batch normalization is a widely used technique in deep learning that stabilizes and accelerates neural network training. By normalizing the inputs of each layer using batch statistics, it prevents large changes in data distribution during training. This improves gradient flow, speeds up convergence, and enhances model stability. Because of these advantages, batch normalization is commonly used in deep neural networks such as CNNs and transformer models. Understanding batch normalization is essential for building efficient and scalable deep learning systems.